All right, folks, it's time for our favorite podcast, Cut to the Chase. We're only missing one thing, my glasses. All right, we're ready to go. So I brought Dr. Adam Liebovich on to talk about nuclear fission. How are you doing today?
Good. I'm doing really great. How are you doing?
I'm all right. That's not completely truthful, but I'm all right, mentally, let's put it that way. Almost, I guess 12 hours ago, we averted a nuclear catastrophe that was not going to be what the show's about. And it's not going to be what the show's about. But I do want to kind of put it in the context of what we're talking about, nuclear fission, because that's been making the news in the last, actually for a long time, but now it's sort of heated up. As many of you know, I'm a climate change guy and nuclear energy. I've always been like, wow, why don't we just go back to nuclear energy? Chernobyl was so long ago, blah, blah, blah. But in any event, there have been advancements that have been made. And I thought I would bring Dr. Liebovich on to discuss those advancements, even talk a little bit about, the nuclear reactor that was taken over by the Russians. What is that nuclear reactor in the context of nuclear energy, nuclear fission? So take it away, Adam. What's going on with nuclear fission? You got
All right. So let me back up a little bit and talk about how we get energy using nuclear particles. So basically, there's two ways we can get energy out of an atom. There is nuclear fission and nuclear fusion. So nuclear fission is what happens in the reactors that we have in the world today. So you take some heavy element like uranium or plutonium, and you break it into pieces. That's what the fission means. So it breaks into smaller pieces, and in so doing, it releases energy. Now, the way it works in a nuclear reactor is these particles, uranium, say, they decay, and when they decay, out comes a whole bunch of particles, and those particles can trigger other uranium atoms to decay further. And so you get what's called a chain reaction of all these particles decaying and releasing energy. So a couple things happen. One, you want to make sure that it doesn't happen too fast, because if it happens too fast, all this energy is released at once and you get a nuclear bomb, like what we dropped on Hiroshima and Nagasaki. So we don't want bombs to go off. So you need to have a way to control the energy. And that's what we do in our nuclear reactors today. They have material which slows down this process enough so that you can control how much energy is being released at a time. Now, that's one way you can get energy from atoms. The other way is called nuclear fusion. So nuclear fusion is what happens in the sun. So in the sun takes hydrogen atoms and fuses them together. So nuclear fusion, they're fusing them together to make helium. You can also fuse other materials together, like helium atoms, to make heavier elements. But basically in the sun, it's taking hydrogen and turning it into helium. So that's nuclear fusion. Now, we have been trying to make nuclear fusion reality on Earth. We can do it, but we can't do it in a way that generates energy. We have to put a lot of energy in, and we can talk about that, but we have to put a lot of energy in to make nuclear fusion works. We can do it, but it takes a lot of energy. The dream is that we get to the point where we get more energy out than we put in which case we can turn hydrogen into helium and get energy out and have no bad radioactive materials left over. So when we have a nuclear reactor like we have now, when all those particles come out, they're radioactive and they will be radioactive for millennia, and it's very worrisome. We have to do something with that. With a nuclear fusion reactor, what comes out is helium, which we have in our balloons and stuff like that. So it's something which is perfectly safe. So it would be the ultimate source of clean energy. So we are really trying, and people have been trying to do this for a long time, to build a nuclear fusion reactor which generates more energy than it puts in. And there is some recent progress on that, which makes us hopeful that in the relatively near future, we may have nuclear fusion reactors, which would be, like I said, the ultimate source of clean energy.
All right, so I want to tell you, I was a history major. That's kind of the way I process information. So in researching this topic, what I came across was 1920s British physicist Arthur Eddington proposed that the sun and stars were powered by fusion into helium. And that proposal basically sparked this research into fusion.
Yes, I mean, there was a lot of things that had to happen in between there, but yes, I mean, it was proposed 100 years ago, roughly, and how the process actually works in the sun was figured out over the next couple of decades. We have a very good understanding of how it works in the sun. To be able to create conditions like the center of the sun on Earth, you might imagine, is kind of difficult. And so that's where the impediment is on trying to recreate that to create energy on Earth.
So was his proposal just sort of lucky, or was it pretty, Eddington, that in the 20s that, the sun and stars were powered by the fusion of hydrogen into helium? Or was it pretty obvious?
Well, it's not obvious at the time, absolutely not. I mean, they were able to look at the sun, and I think we've talked about it before. Different elements will give off particular types of light, the spectrum of light that comes out, certain wavelengths. So they knew when they looked at the sun that it was basically a ball of hydrogen and helium. That's pretty much what they could tell. So he knew that. And they also knew from the periodic table what hydrogen is, what helium is. Hydrogen is basically a proton with electrons around it. Helium is nucleus, which has 2 protons and 2 neutrons with electrons around it. So the idea that that you could gain energy out of combining hydrogen particles together to make helium was something that came out of Einstein's theory of relativity, E equals mc squared. So all of that was in the milieu at the time when they were coming up with these new theories back 100 years ago. So it was definitely not obvious. Someone had to put all the pieces together. And then once you had the idea, it wasn't, obviously right. And you had to do a lot of investigation to see whether it was true. But he was right. And now we have a very good understanding, like I said. So. Okay,
so there's 4 more historical facts on this that I sort of want to touch base on, in connection with nuclear, this advancement in nuclear fusion. Number 1, we grew up, we were learning history about World War II, and they dropped, the United States dropped the atom bomb. And, I was like, all right, they dropped the bomb, and I'm thinking, whatever, it was a bomb full of atoms. I didn't know. And, then all of a sudden there was a nuclear bomb. There was like, oh, then everybody's running in the shelters, the Soviet Union, nuclear bombs. How is the atomic bomb scientifically, in context of physics, different than the nuclear bombs that went, the initial ones?
Right. So really saying an atomic bomb and a nuclear bomb are basically saying the same thing. So there's a core, which is usually plutonium, which if you compress it down tight enough will cause one of these chain reactions that I mentioned before. And in this case, it's not a controlled chain reaction, and it releases a ton of energy. Now you can build big ones or medium-sized ones, whatever it is, it's going to let off an unbelievable amount of energy. There is something called a hydrogen bomb, which came out after the original bombs, like the ones that were built during World War II. And a hydrogen bomb essentially is a nuclear bomb, like the ones that we had in World War II, but also with basically amount of hydrogen in there as well. And when the nuclear bomb goes off, it creates essentially the center of the sun, and it combines those hydrogen atoms into helium. So a normal nuclear bomb works by nuclear fission. A hydrogen bomb works by nuclear fission and nuclear fusion, which causes just so much more energy to be released.
All right, so these bombs are essentially releasing energy, and the concept of like a nuclear power plant is that energy is not getting released. That energy is essentially getting controlled, and it's being released as civilian energy. They've developed reactors that send out through the grid this energy in a controlled fashion.
Right. It's basically a nuclear bomb, but without the bomb part, without the boom part. You have the same process going on, but you don't allow a runaway chain reaction. You have it in a nice controlled manner.
All right. So, and one of the problems with fission, the nuclear fission, the reactors that we have right now, is that there's waste,
Yes.
and problems not just in general, but also impediments to using nuclear energy globally, and just ending the whole climate change discussion in the context of, can we get an emission-free nuclear energy source? So you have the waste is a problem. You have the cost of building these reactors and the amount of time that it takes to build these reactors. But the nuclear fission promises to essentially, if we could develop it even further, there would be no waste, and can you develop it quicker and cheaper, or do we still have those kind of impediments?
It will cost a lot of energy, especially initially, once we get to the point where we know how to generate energy out of the process. So I'm not going to sugarcoat this. This is going to cost a lot of energy to build a fusion reactor, but once we figure it out, I'm sure there'll be ways that costs will get driven down and so on. And in the grand scheme of things, it's going to be a lot cheaper to build a bunch of fusion reactors than dealing with climate change. So we would be able to totally electrify the automotive industry and so on, and we would be able to remove ourselves from fossil fuels. So it would definitely be the right thing to do once we get to that point. Now, I should say that we're not there yet. There's been this saying that we're always 30 years away from nuclear fusion. People have been saying that for decades, but there's been a lot of progress recently. So it's actually looking like we may be getting there. So that's the exciting news.
All right, so the big money is pushing this. Bill Gates, MIT, apparently 35 nations are collaborating to build and operate the ITER Tomac, which would be the most complex machine ever designed to prove that fusion is a viable source. So right now, basically, it's taking more energy. The whole, if we want to do nuclear fission, it takes more energy than we create.
Right. So the way we can make things fuse together is by compressing essentially hydrogen really, really close together, because they don't want to come close together. two protons, they're negatively charged. It takes a lot of energy to get them close enough so that they suddenly would fuse together. And there's two basic ways that we know of to cause the hydrogens to get close together enough. One is called it's basically magnetic confinement. You put the hydrogen gas in essentially a magnetic bottle, and you heat it up really, really hot. And so it's hot, so these particles are bouncing off each other because it's so hot. So this is like in the center of the sun, but you need to contain it because hot things would disperse. And so you confine it in basically a magnetic bottle. And that's what that tokamak that you mentioned is. It's a very fancy type of bottle, which is caused by magnetic fields, which contains the gas inside it. So that's one way you can do it. There's also what's called inertial confinement. And this is another way that people are working on to cause fusion. And in this case, they have little pellets and they send lasers in from all directions, and it causes the pellet to basically vaporize and compress down into the center. And in so doing, they can cause nuclear fusion in that as well. So these are two competing technologies that we have right now. Both have made progress recently, getting us closer to the point where we might be able to get energy out. And which one's going to win out, or if they both win out, is sort of unknown at this point. The ITER facility, so that stands for the International Thermonuclear Experimental Reactor, is being built in France. It should be completed in a few years. It's actually 3 or 4 years off, I think, for when it's supposed to be constructed. And they potentially have the ability to get to that point. We will have to see, and it might take a little while for them to work out all the bugs, but the design is that they will get to the point where they will be able to gain energy out of the system.
All right, so two of the arguments against solar and wind as renewable energy are that you got to have the sun going, and then, where are you going to store the excess batteries and all that? But from what I understand, nuclear fusion is almost limitless, would be almost limitless if we could get to the point where, we're able to make it in a feasible way.
Yes, basically limitless. You basically can get the raw materials out of the ocean, and there's plenty of ocean. We wouldn't be destroying the oceans. There's no worry about that. And it's essentially would be limitless.
Yeah. All right. So nuclear energy has existed and been in effect for decades now. And, some people maybe are like, well, it's a no-brainer. Let's get nuclear energy. What are we waiting for? But I mean, we've had decades, and I say the world has been debating nuclear energy for decades. And Germany has had nuclear energy. They are I don't know if they're completely phased out, but they are basically saying no to it. And some of the nuclear plants in the United States, are being phased out. It's too costly. And in the environmental movement, there's no consensus. I think this latest issue is going to raise the stakes a little, the debate even more. But my understanding is that nuclear fusion. All right. So before I even go on to that point, I want Chernobyl and Fukushima.
Yes.
The nuclear power plants back in the 80s. What happened to them? They blew up. They melted down.
Right. So two different situations. In Chernobyl, they had some issues. I don't remember exactly what the issue was. I think it was like a bad signal, and things got out of hand essentially. But the system lost the ability to control the nuclear reaction. So instead of being a nice controlled nuclear fission reactor going on, it essentially turned into basically a small bomb. There was heat up of gas, and it blew out of the top, released a ton of radioactive material into the atmosphere, essentially caused the area to be evacuated. So people had to leave their houses for miles and miles around. And it was similar to, but much worse than what happened in 3 Mile Island. 3 Mile Island is also sort of one of these situations where there was a nuclear accident, although in 3 Mile Island, it wasn't nearly as bad as what happened in Chernobyl. Fukushima was a little different. That happened 10-ish years ago now in Japan, and there was an earthquake off the coast of Japan, which caused a tsunami, and the wave came in and it knocked out the power and the reserve power that went into controlling the power plant. And again, they had this problem of the nuclear core melting down. So neither were good. Both of them released radioactive material into the environment. Chernobyl was much worse. And I should say that there are much safer. Chernobyl was a fairly early generation nuclear reactor. There are much safer designs nowadays, which means that when the power goes out, the whole thing would just shut itself off, rather than what happened in these situations. So you can design them so that they are much safer, and it is a way to get rid of carbon. So we would not be releasing carbon dioxide, but you do still have the problem that in the end, after your nuclear fusion is done, you have these very radioactive materials around, and you have to do something for them, and they will be radioactive for millennia. So you have to basically figure out how to store these really dangerous materials for a long time. And that is really the main problem nowadays with nuclear fission. So the traditional nuclear reactor, you would not have that problem with nuclear fusion though.
Okay, and I think the other additional benefit of nuclear fusion is it does not lend itself to meltdowns.
Right, so if there is a problem, what would happen was the magnetic field in the magnetic confinement type, the magnetic field would disappear and the gas would blow out, and that would be it. And there's no radioactive material to begin with, so you would just, it would shut itself off. In the inertial confinement, if the lasers turn off, then nothing happens. So in both situations, there's not really this worry of some uncontrollable disaster happening, which is definitely a worry with a traditional nuclear reactor.
All right, so yeah, the traditional nuclear reactor and the environmentalists or the people that were anti-nukes were basically saying, hey, the design, could be defective and cause all this radioactive material all over the world, number one. And now, then you have natural disasters, tsunamis, I guess they didn't really prepare for that, or maybe they did or whatever. And now you have the geopolitical concern. So
right.
I'm going to put it to you right now. Do you think if they can get nuclear reactors, nuclear fusion, is that something that lends itself to geopolitical terrorism?
Certainly not in the same way as our nuclear reactors today. I mean, if the worst you could do with a fusion reactor is shut it down, which, they could hack into the system and shut the thing down.
Yeah.
Okay, so we have blackouts, which, could cause some serious problems, right? But it wouldn't have the same potential disastrous effects that we have with nuclear reactors. So you could imagine really bad players going and stealing spent nuclear rods and making a dirty bomb, right? That's a possibility that, you know, you have to take seriously. But with a fusion reactor, that would not be it would not be a possibility. It's just not a possibility. So
Yeah. All right. Well, I'm predicting that this latest issue is going to be, you know, something that gets in the way of moving this forward. But you know, there's a lot of money, and I think that, you know, the people like Bill Gates and MIT, they're going to go forward nonetheless, and just hope at some point that, you know, their message about how much safer it is gonna ring true.
yeah, as soon as we have a viable system, people will start to build them for the public power supply. It's really a no-brainer once you get to the point where you figure out how to have a sustained energy output. And realistically, both of these strategies to try to make fusion work are getting much closer to that. And ITER in particular, which is supposed to be up and running in this decade, they basically are just scaling up systems that they have now, which are just on a much smaller scale. And in that scale up, they can predict roughly how that will translate to energy output. And so it really should work. And I'm sure they'll have to figure out a whole bunch of things, but it should get us to the point where we have a actual nuclear fusion reactor. So
my understanding is that they're, you know, basically developing, instead of having this humongous reactor, they're going to do little mini reactors, and they're going to make it in a way which are like modules where, you know, it's almost like you buy a franchise and you just pop it up wherever you want to, and away we go.
That would be the ultimate goal. We're a long way from that right now. So we need to actually get to the point where we figure out a way to make it sustainable. Obviously, that would be the best thing to do. You know, then you could have small nuclear fusion reactors spread out to distribute the energy production, which of course is much safer and better for the energy grid, and so on and so forth. So that would be the ultimate goal. Right now, we're not there yet, certainly. And the joke that we're always 30 years away, hopefully we're actually a real 30 years away till that vision comes true.
All right, that'll be the last word. Adam, thank you very much. Hopefully in our lifetime, we're going to get peace, and we're going to get limitless energy from this.
That would be the goal. That would be great.
Nuclear fusion, the artificial sun on Earth. All right, that will do it for this episode during these trying times of Cut to the Chase. And there's no CTA, there's no call to action aside from, you know, heads up and be careful, be safe, and God bless the earth, I guess. So Adam, take care of yourself, and we'll circle back to our next topic shortly. All right.
All right, sounds good. Nice talking to you.
All right, everybody, take care.